Higher derivatives. Alright, this is actually a really nice lesson because higher derivatives are derivatives obtained by repeatedly differentiating a function y equals f of x. So let's take a look at what we would mean by the second derivative. So if f and f prime are differentiable, then the second derivative is the derivative of the first derivative. So f double prime of x is how this is read, equals the derivative d dx of f prime of x. So it's the derivative of the first derivative gets us to the second derivative. So f double prime of x. And an alternative notation would be y double prime or d dx of dy dx. So the derivative with respect to x of the derivative function dy dx. Or, here's what's new, we can also write this as d, and it looks like squared, so it kind of looks like d squared y over dx squared. But really, it's not read like that. It is read as the second derivative of y with respect to x. So the 2's are just indicating that we are stopping at the second derivative. So now let's go ahead and take a look at an example. So in this example, we're being asked to find f double prime of x given f of x equals x cubed minus 3x squared plus 2. So the first thing we need to do is find the first derivative. So this is a nice one. We can use the power rule. We're going to get 3x squared minus 6x, and the derivative of 2 is 0. So here's my first derivative. And the second derivative is just the derivative of the first derivative. So the derivative of 3x squared is 6x, and the derivative of minus 6x is minus 6. So that's all there is to it. The second derivative is just the derivative of the first derivative. So what we did to find the second derivative wasn't unique. We can continue to do so to find higher derivatives. So the higher derivatives are considered f double prime of x or f triple prime of x, and they are defined by successive differentiation. So again, the second derivative is the derivative of the first derivative, and the third derivative, so the notation here is, again, that 3 in the exponent position tells us the third derivative, or f triple prime of x, is the derivative with respect to x of the second derivative. And we can keep going with this. So the nth derivative, and once we get past 3, we don't really continue to use the little tick mark, so we wouldn't write f and then put 4 little tick marks. The second we get past 3, we're going to use this notation. So f to the, and then n would be the number of derivatives you're taking, so 4 or higher would go here, of x, or we can use the other notation where the derivative we're trying to find goes in the exponent in the numerator of the d and then in the denominator of the x. So both of these are equivalent notations for finding higher derivatives using successive differentiation. Alright, so let's do a couple examples. We want to find f triple prime of x given f of x equals x squared minus 3x plus 5. So first we find f prime of x. Using the power rule, we're going to obtain 2x minus 3. Now we have to find f double prime of x. So the derivative of 2x minus 3 would be just 2. So f triple prime of x, the derivative of a constant function, so this is a horizontal line, which has slope 0, so the derivative is 0. And any derivative after the third derivative here would continue to be 0. And let's go ahead and take a look at one more example. Here we want to find the fourth derivative given f of x equals 1 over x. So here's what we should definitely not do, is use the quotient rule, because then I might be forced to think that I have to use the quotient rule over and over again to find the fourth derivative. So what I should do is recognize that 1 over x is x to the negative 1. So here, let's go ahead and take the first derivative. So bring the power to the front, the negative 1, x to the negative 2 if I subtract 1 from negative 1, f double prime of x. So negative 2 times the negative in front is going to give me a positive 2. And then I'm going to have x to the negative 3. f triple prime of x. The negative 3 times the 2 in front is going to give me a negative 6, x to the negative 4. And then to find the fourth derivative at x, which is what I was originally searching for, I'm going to have negative 4 times negative 6, so positive 24, x to the negative 5. And if I wanted to rewrite this so it did not have negative exponents, we'd have, whoops, not 25, sorry about that, 24 over x to the 5th. Now the point I want to make here is that the previous problem, it might have seemed like no matter what, if we continue to take derivatives over and over again using successive differentiation, we're always going to hit 0, right? Well, in the case of a polynomial, yes. In the case of a polynomial, which is variables raised to positive or to whole number exponents, we are always going to eventually get 0 if we keep going with successive differentiation. But this is not a polynomial. This is a rational function here. And if I keep going, I'm not going to get to 0. And there are other functions too, such that successive differentiation does not result in eventually getting 0 out as a derivative. So I just wanted to clarify that. But other than that, higher derivatives are pretty intuitive. Again, you just keep taking the derivative over and over again until you get to the desired results.